Alright, let's take another example. Let's make this one a little more interesting. I'm going to have an incline, and there's going to be a pulley here at the top of the incline, and a mass hanging up here. I'm going to call this mass 1. And then down here, I'm going to have another mass, make that mass 2, and mass 2 is going to be attached to a spring. Now to make life easy, let's have the spring at equilibrium when I start this problem. So what I'm interested in is the energy bar graph for this situation. So it's going to start at equilibrium, and it's going to start at rest. It starts at equilibrium, and that makes my spring nice, and it's going to start at rest. So that makes my kinetic energy nice. So the energy bar graph is going to look like this. Kinetic energy, now I'm going to say kinetic energy 1, because that's mass 1's kinetic energy. And kinetic energy 2, these are both 0 because it starts from rest. There is a spring potential energy, and that's equal to 0 because I started from equilibrium. But then what's interesting now is the gravitational potential energy. The datum can be wherever I want it. So the datum for this one, I'm going to make that equal to 0. So that's equal to 0. I'll call that y2. And then this is the datum, y1 equal to 0. So notice the datum for mass 1 and mass 2 are not the same place. They could be. I could set my datum here equal to 0 if I so desired, and life would work out just fine, but the mathematics is not quite as nice. And so I'm going to end up with two gravitational potential energies, so Vg1 and Vg2. And since I'm starting at the datum, all of these are equal to 0. So I have 0 bars total in this scenario. Now what happens is mass 1 falls, mass 2 rises, and the spring becomes stretched. So at some later point, there might be some kinetic energy 1, make that 1 bar. Block 2 has some kinetic energy 2. Let's make block 1 have 2 bars. Maybe it's the heavier one. And block 2 has 1 bar. There's some spring potential energy. We'll give that 2 bars. And then there must be, let's call that angle theta. So then the gravitational potential energy for 1, it's falling. So maybe it's fallen 4 bars. We'll find out in a second that's not going to work. So that's V gravitational 1. And then there's gravitational 2. Now it's going up. It's lighter, so let's say it goes up 2 bars. Now remember, the distance it rises, it's going to move. Let's say it moves a distance delta S down. This is going to move a distance delta S up the incline. But what that means is that the distance it rises is delta S times the sine of theta. All right, so I've got 1, 2, 3, 4, 5, 6, 7 positive bars, so this has got to have 7 negative bars. So 1 more. I've got to have a total of 0 bars. And so my equation would look something like this. 0 equals 1/2 mass 1 speed 1 squared plus 1/2 mass 2 speed 2 squared. But before we go too much farther, 1 and 2 are connected by a string that goes around a single pulley. They had to have moved the same distance over the same amount of time. So V1 and V2 are the same, so I'm just going to call that V. And here's the spring potential energy, so plus 1/2 K delta S squared, because that's how far the spring has stretched as this mass goes up the incline a distance delta S, minus M1 G delta S, minus, because it's falling downward, plus M2 G delta S sine theta. That's how far up mass 2 rose. And so this is my energy equation. And there might come a point in time where the two masses stop. In that scenario, G1 will have fallen farther. These will both have risen a little bit, but these will have gone down to 0 because they've stopped. Talk just a little bit about potential energy curves. This is already drawn in, but here's a graph of potential energy. Okay, I'm using U for potential energy here. Notice I've interchanged U and V quite a bit. That's something you need to get used to. We'll say that U is a function of position, so here's position over here. So that function of position would be this black curve that you see right here, and these red energy curves would be the total energy of the system. So this might be, say, a skier moving up and down a slope, or a roller coaster moving up and down the slope. If the roller coaster has some energy E1 higher than all of these hills, the roller coaster will continue to move. But if it has an energy E3, say in this area, it can never get to this location because the roller coaster cannot have more potential energy than the total energy of the system, assuming the potential energy is always positive. Okay, so some points of interest. C is a point that we refer to as a point of unstable equilibrium, meaning the roller coaster cart, could be here, not moving. And if it's there not moving, it's going to stay there not moving. But if I give it just a little bit of a push left or right, it's going to begin to roll. So it's at equilibrium, but it's unstable. Another situation with unstable equilibrium, try to balance your pen straight up and down. It's possible for it to happen, but it's very difficult. Position A is a position referred to as stable equilibrium because if I put the cart right here and I give it a little nudge to the left or a little nudge to the right, it pretty much stays at the A position. And so it's stable in that location. These are regions of unstable and stable equilibrium. Okay, so what do I do in a system where there are non-conservative forces taking place? How do I do the energy bar graphs from there? And another question that we might ask and answer is, where does the energy go to and where does it come from in a system where there's going to be a non-conservative force? A couple of examples of where energy might go to would be, say, friction. If you have an object sliding up an incline or down an incline, as we're about to do, then that energy that's lost goes into another form of energy, because you can neither create nor destroy energy, but it goes into a form of energy, generally heat. And so we're not able to use that energy in a simple system. Maybe in a complex system we can. Another example might be, let's say, an astronaut using a jetpack. So the astronaut's on the ground, potential energy is 0 from gravity because he's on the ground, kinetic energy is 0. But then he boosts himself up and he's moving up with the jetpack, so now he has positive potential energy, positive kinetic energy, but his total energy should be 0. Well, so where'd that energy come from? It comes from the jetpack, and that's a conversion of chemical potential energy into gravitational potential energy and kinetic energy. So we're just going to do a real simple example. So here I have a 50-pound package sliding up an incline at 20 degrees, and it's going to start off down here at position A. So the velocity at A here is equal to 40 feet per second. The coefficient of kinetic friction between the package and the incline is 0.15. So some energy is going to be lost due to friction. That's what we're going to have to account for. So what we're going to start off with is the maximum distance x up the incline that the package will slide. Because there's going to come a point in time where it stops. So the velocity at B is equal to 0. I need that. It's not stated, but it's understood based on the sentence structure that the package is going to stop at the maximum distance x. So if I look at the potential energy at A, I'm going to actually let the potential energy here at A equal 0. So this is my datum. So y is equal to 0. So it's got some kinetic energy. Let's give that 3 bars of kinetic energy. But it has no gravitational potential energy. Then over here at B, it's got no kinetic energy, but it is going to have some gravitational potential energy. Now here's the interesting thing here. I'm going to put in 3 bars. But the idea here is that had there been no friction, it would have had more potential energy. It would have continued up farther than it does at point B. If there was no friction, the kinetic energy and the potential energy would be the same. But because there is friction, it doesn't go up as high. So if it's not as high, then the gravitational potential energy can't be 3 bars. So something's kind of weird here. And what's weird is that there's 2 bars over here, and there's 3 bars over here on the left. So I can't have that. I want only 2 bars. And so what I'm going to do is I'm going to say, well, there's going to be some work done, and I'm just going to use W for work, and I'm going to subscript it as non. This is work done by non-conservative forces, and I'm going to make that a -1 bar. And now I've got 2 bars, and now I've got 2 bars on both sides. And so 1/2 mv at A squared minus the work done by non-conservative forces, in this case friction, must equal mgy at B. Well, I'm not going to go into too much detail. Suffice it to say the normal force is equal to mg cosine theta, and so the frictional force equals the kinetic frictional coefficient times the normal force, mg cosine theta. And so it moves the distance x up the incline, so this becomes 1/2 m v at a squared minus, and it's really, you can think about it, it is negative because the force is down the incline, the frictional force. The displacement is up the incline, and so the work has to be negative. That's why it's over here on the left. And so I'm going to get minus mu mg cosine theta x. And that's going to equal the potential energy, which is mg y sub b, but y sub b is x sine theta. And so if I put in numbers, just so you can see how this works, 1/2, the mass is 50 pounds over 32.17 feet per second squared. That's going to be the mass in slugs. And then 40 feet per second squared minus 0.15. This is mg, so that's 50 pounds. Cosine 20 degrees times x, that's what I'm looking for. And that's all going to equal 50 pounds times x times the sine 20 degrees. So x is the only unknown, so I can solve this equation for x. Okay, then the velocity of the package as it returns to its initial position. So now it's going to slide back down the incline. So I'm going to start with this energy bar graph. And this gets a little tricky here. So at B, it's got no kinetic energy, and it's got 2 bars of gravitational potential energy. But it's going back down the incline now. So the displacement is down, the frictional force is up. I'm going to have negative work again. So the work done in non-conservative forces, I'm going to make that a negative 1 bar. So I have a total of 1 bar of energy. Then at position A, when it's at the bottom of the incline, it's going to have a certain amount of kinetic energy, but it's not going to have any gravitational potential energy anymore. So I have 1 bar over here, this is going to be 1 bar. So you can see it's less than it had before. So I have mg times the height, which was x, which we now know because we've solved for that, sine theta minus mu mg cosine theta times x. That's the work done by the non-conservative force. And that's going to equal 1/2 the mass times the velocity at a squared. Now this is not going to be the 40 feet per second I started with. It's going to have lost a certain amount of kinetic energy, so it's going to be slower. If I put in numbers, I'm going to get 50 pounds times x, which I know from the first one, sine 20 degrees, minus 0.15, 50 pounds, cosine 20 degrees, times x, which I know from part A, equals 1/2 50 pounds over 32.17 feet per second squared, times the new velocity at a squared. Keep in mind, I know this and I know this. The only thing I don't know in this equation is right there. Okay, part C was the total amount of energy dissipated by friction. This was energy dissipated by friction, and this was energy dissipated by friction. So if we put those together, we can find the total amount of energy dissipated by friction. All right, I just want to do one more example. Let's say this is the potential energy function, squared y cubed. I'm interested in the force. So here's the force equation. Remember that the force was equal to minus the gradient of u. So the gradient is the partial with respect to x in the I direction plus the partial with respect to y in the j direction acting on this function. So the partial with respect to x of x squared y cubed, we pretend y is a constant. So the derivative of x squared is just 2x. Y is a constant because it's a partial derivative. You'll learn more about that when we get there. Don't forget the I hat. This is a vector quantity. Then I take that same x squared y cubed and I take a partial with respect to y. So I pretend x is a constant. So x squared stays x squared. Derivative of y cubed is 3y squared. That's in the j hat direction. And so this becomes the force that is associated with this potential energy. And that's how we do partial derivatives.